So in our last segment, we developed the Biot-Savart law, and we wrote this down in two forms. The first of these forms, this one here, the top one, is applicable to line currents where we're integrating in one dimension. The second equation is actually applicable in all situations. The first equation is a special case of a three-dimensional current density J. Now I'm going to show you that in a later clip, but for this particular segment we're going to be dealing with a line current. And what we're going to do is we're going to calculate a classic problem in magnetostatics, that is the magnetic field above a circular current carrying loop on axis along the axis of cylindrical symmetry of the problem. We're going to do this problem in a rather general way, and I'm going to show you the techniques involved in solving the problem. The techniques that I'll show you are applicable to far more difficult problems, and so it's useful to study those techniques in a simple setting. Okay, so here then is our problem. We have a current carrying wire. It's just a circular loop of radius r. It's carrying current I, and it's carrying the current in a counterclockwise direction if we were to look down on the loop. We're interested in the magnetic field at this point here, which is a distance z hat above the center of the loop. This is on axis, on the symmetry axis of the loop, directly above the center. We'd like to know what is the magnetic field. The first step in a calculation of this kind is to write down the equation that we're going to use. So we have this equation over here for the magnetic field, and at this point really all we need to do is to identify the elements inside this integral, write them down, and then construct this thing and do the calculations. So when you first look at a formula of this kind, it can look a little complicated. We've got a cross product, we've got a length element, unit vectors and so on, but you'll see that if we construct this in a methodical way, it becomes a straightforward calculation. So let's do that. Okay, so here then are all our elements. I've written down dl prime. Now I'm using cylindrical coordinates. Here is our dl prime. It is in the direction phi hat. I identified phi hat on the diagram in the previous page. So this is the cylindrical unit vector in the phi direction. dl prime in magnitude is given by the radius of the circle multiplied by d phi prime. This will become our integration variable. R, on the other hand, is our point of observation. So R is z hat. We're interested in the magnetic field at distance z above the center of the circle. R prime is a vector, a position vector, that points to our source term. So R prime points to our element dl prime. You'll notice that the only component of R prime is a rho hat component. This is important. There is no phi hat component in the position vector in cylindrical coordinates ever. There is never a phi hat component, and because we're at z equals 0, we're in the xy plane, there is no z hat component to this position vector. If I subtract r prime from r, I get this result here quite clearly. If I take the mod square of that vector, in other words I'm looking for the squared length of the vector, because rho hat and z hat are perpendicular, it is simply z squared plus r squared, and by taking the square root of this quantity and normalizing my r minus r prime vector, I get the unit vector. Okay, so these are all the bits that we need. All we have to do now is to put it all together. Now before we put it together, let's calculate these cross products. We're going to need a cross product of dl prime cross r minus r prime hat. And if we look at that, our dl prime is in the phi hat direction, and this unit vector has a z hat component and a phi hat and a rho hat component. So we're going to need to take two cross products, phi hat cross z hat and phi hat cross rho hat. So let's do that. We'll just use the right hand rule to do that. Let's do that now. Okay, so there are those two cross products. Check that using the right hand rule just to convince yourself that this is in fact correct. And now we can begin to put the whole lot together. Perhaps we'll start on the next page by calculating, well, we'll calculate the full integrand here. Let's do that. Okay, so here then is our integrand. You'll notice that we've completed the cross products as we outlined on the previous page. Bear in mind that this cross product was minus z hat, and so combined with this minus sign we get a plus z hat. The z squared plus z squared plus r squared to the 3 halves contains two contributions. One of them comes from this quantity here. The other one, of course, the other factor comes from the normalization of this unit vector. So this is where the 3 halves comes from. You'll notice that our integration variable is going to be over d phi prime, and everything in this integrand is constant except for one item. And that one item is the rho hat unit vector. So the rho hat unit vector varies as we move around the circle. So we can draw the circle, and as we move around phi prime in our integration, our rho hat unit vector is going to change. It's a function of position. And all the contributions from the rho hat part of this integrand are going to cancel. They're going to cancel because everything else in the equation is constant. So we can neglect this term here just by considerations of symmetry. Everything else in this equation is now a constant. And we can actually do the integral in our head. The integral over d phi prime is just going to be a factor of 2 pi and nothing else. Now, in a later segment, I'm going to show you formally how to do the integral over rho hat so that we don't have to rely on considerations of symmetry. Both techniques are very, very useful. If you can see by symmetry it's going to be 0, get rid of it. If it's unclear, I'll show you how to do this formally, symbolically or mathematically. But let's save that for a later time. At the moment we're going to deal with just this part of the integrand. So let's complete that. Okay, so that completes our calculation. The integral, as I said, is just over d phi prime. This is a factor of 2 pi, which cancels, of course, this pi and one factor of 2. We're left with the 2 downstairs here. Our magnetic field is proportional to the current. It's linear in the current. It's in the z hat direction. And it's a slightly complicated function, both of the radius of the loop, r squared, and the distance away. In the next segment, we're going to study this magnetic field in two asymptotic limits. We're going to look at the limit when z is very small compared to r, that is, we're close to the center of the circle, and when z is very, very far from the center of the circle, that is, z much, much larger than r.